So can you hear me on YouTube? Yeah. I hope I can hear well on Google Meet. Speak up someone one more time. Yeah. An ideal gas. I mean, this is, I think, it was there in CSIR as well as just also. I hope so. I mean, it is a bit general problem. Okay. I mean, even if you remember some output, that would be better. Okay. Speak up. So part of the question, I mean, one integral. Am I right? If you have tried one integral, that was also one question in CSIR-NET exam. Okay. I mean, that was bit unexpected, that particular question. But you could have eliminated answer by knowing the special integrals. I mean, you know, a Gaussian integral, you know, exponential integral, 0 to infinity e power minus ax. Am I right? So using those, I think you could have eliminated answers. Okay, that's how they designed the question actually. Okay, now let us start solving this one. Okay, an ideal gas of particle each of mass m at temperature tau. Actually, in the textbook you may have bit confusion. I think that KBT together he will call it as a tau, very old notation. Okay, but let us take KBT here. Okay, speaker. Is subjected to an external force whose potential energy. That means you have a ideal gas here. Okay, speak up. I mean, there. I mean, ideal gas means there is no interaction between the particle. Is that okay? Speak up. You have particles, so there is no interaction between the particle. Okay, so but it is somehow acted upon by the external force, external field. That means each and every particle possessing this what you call potential. Okay, speak up. But only one they have to mention the dimension. Am I right? It is a bit confusing for me right now. You have to take three dimension. Once they say ideal gas, you have to take three dimension. But force is applied maybe in only one direction. Can I take like this? Speak up. X, Y, Z. Okay. Speak up. Force is applied only one direction. Let me take like this. I mean, force means, I mean, your potential depends only on the function of x, isn't it? Speak up. So let me check out.
Getting the given one-dimensional potential.
Hmm?
Getting the mentioned one-dimensional potential.
Okay. He mentioned one dimension. One dimension. Then we should not take this whole diagram at all. I mean, this is three dimension. Is that okay? Speak up. Ideal gas in one dimensional potential. That's right. Okay. Speak up. Yeah. Anyway, he's asking find the average potential energy, and again average potential energy per particle when in the uniform gravitational field. I mean, if they ask total average energy, other dimension does matter. I mean, kinetic energy, whether it is two dimension, three dimension. He's asking only about this one, right? Speak up. So now what I do here is speak up. I mean, while doing this problem, we can do in many different ways. Yeah, let us do like this. Okay, I mean, he has given u of x is equal to pick up a x power n. Okay, x is between 0 to infinity. Okay, speak up. Anyway, let me take all of these particles are in one dimension. Okay, there is nothing wrong. Even if you take three dimension, that's also works actually. Nothing wrong. Okay, speak up, because he said one dimensional potential. Am I right?
Could be that the gas is 3D.
Gas is 3D, force in one dimension. Okay, let it be. Let us take one dimension because it doesn't matter. In that ratio, while finding the average, the rest of the terms will get cancelled. I hope right now you have sufficient experience over there. Okay, speak up. Now find the average potential energy. That's what he's asking. That average potential energy, U of x. Okay, U of x. Okay, that's equal to. So U of x into e power minus beta e. Okay, so dx dpx, I'll take only, I mean, if I take energy, is equal to px square by 2m. Okay, I mean individual particle energy. Okay, so plus a x power n. I mean, suppose it's a one-dimensional gas. I mean, I'll assume like this. Okay, if I take like this is constant into this one. Okay, there's a probability factor integral. Speak up, e power minus beta a. So dx into dpx. That when you write energy, when you separate, that px part of the integral will get cancelled. Like that, even if you have three-dimensional one, px square by 2m, py square by 2m, okay, that will get cancelled. So dy dz, that integral is common actually. Only x integral is not common. You can see that one, isn't it? Pick up. So that's why I hope, I mean, this normalization constant is also common. I hope you can quickly write this expression. Okay, integral 0 to infinity, x is ranging from 0 to infinity, a x power n e power minus beta a x power n, okay, into dx whole divided by integral 0 to infinity e power minus beta a x power n dx. Have you written this one? I mean, you should quickly get into this step actually, because whether you take two dimension, three dimension, or only one dimension, other part of the integrals will get cancelled. If you take three dimension, actually dy dz also should come. That also common. Okay, only x part of the integral is not common. Okay, I hope you guys have enough experience here. Okay, pick up in the textbook. I think he solved in bit different way using, I think, Helmholtz free energy and all, but it's not required. Again, average energy. Am I right? We just need average energy. Sorry, average potential energy. Now this integral, am I right? We just need to work on this integral. What are the integrals we have? Integral 0 to infinity. Now, one thing that you can do is you can write in terms of some derivative here to avoid. Okay, speak up. How do you write? Speak up. Average u of x, that's equal to 0 to infinity minus dou by dou beta of, okay, speak up, e power minus beta a x power n into dx, okay, whole divided by 0 to infinity e power minus beta a x power n dx. Am I right? Speak up. I mean, this is a usual trick that we did in from reef actually. Okay, speak up. So now what is this one? I think I can take. Wait a second. When I take it outside, it will be d by d beta. Here it is a partial derivative. When I take it outside, speak up. X variable will not be there inside. Am I right? Speak up. Just think over it. Or let me write minus dou by dou beta. I mean, I hope it will be function of beta only. Okay, speak up. Integral 0 to infinity e power minus beta a x power n dx whole divided by integral 0 to infinity e power minus beta a x power n dx. Okay, because he mentioned only this integral, not this integral. I mean, that a x power n multiplied with e power term, that's not mentioned. Okay, speak up. Now this can be written as minus dou by dou beta of log of, okay, integral 0 to infinity, so e power minus beta a x power n dx. Am I right? Isn't it? Hmm?
Here, can you take the log inside?
Oh, how you take log in? No, no, no. Log of addition. I mean, you think it as a summation. Log of a plus b plus c. Will you write log of a plus log of b? No, log of a into log of b. Isn't it? Speak up. That's not possible. Okay, speak up. Now only one integral is left here. That is what is that? So integral, I'll write 0 to infinity e power minus a x power n. Okay, dx. I'll write like this. Later we can convert, isn't it? I mean, you can add this one to your integration table. Okay, but look at here. The question was given in such a way that you know for n equal to 1, you know the integral. For n equal to 2 also, you know the integral. Using those two, you can eliminate options. Speak up. I mean, I told you one day, am I right? Special case. You know the special case. They will ask some general question. You know the special case. Apply the special case. If you can eliminate the option, eliminate the option. Don't try to do it in ideal way. Okay. Anyway, this may be a bit lengthy. I mean, to prove this one. Okay. How it is. I mean, it's a kind of gamma integral only. Now, this is equal to 1 by. Give me a minute. gamma of 1 by n, okay, that is one factor. Give me 1 minute, okay, let me just write down first. Gamma of 1 by n, okay, how do we write? Gamma of 1 by n, okay, speak up, multiplied with 1 by n gamma 1 by n, okay, speak up, 1 by n gamma 1 by n, okay, and along with that one, a by 2 1 by a, okay, 1 by a power 1 by n, power 1 by n, speak up. Now you may not know this gamma of 1 by n always. That you if you can convert that gamma of 1 by n into gamma of half is root 5, that you know. Am I right? Pick up. Gamma of half, so that's equal to root 5, that's you know. Suppose gamma of 1/3, you don't know. Speak up. But leave it, it's a constant. Okay. I mean, you have to take a log of this one and then you need to take a derivative. Okay, speak up. It doesn't matter what is the exact value of this one. Is that okay? Pick up. When n equal to 2, you know what is the value. When n equal to 3 and other value, you don't know the value actually. Okay, I mean, that's again different mathematics. Is that okay? Speak up. So can you note this down? Wait a second, let me verify. 1 by n gamma 1 by n, that's right. Okay. A by 2 1 by, yeah, this is right. Okay, speak up. So now this integral is integral 0 to infinity e power minus beta a x power n dx. Am I right? Speak up. So this is equal to 1 by, so beta a whole power 1 by n, okay, 1 by n gamma 1 by n, okay, speak up. Now since you need to take a log, isn't it, you can separate all constant one side, isn't it? Speak up. So that means beta power minus 1 by n, that's one side, okay, into rest of all are constant. Can I write like this? Pick up 1 by n a power 1 by a power 1 by n into n gamma of 1 by n. Okay, this whole thing is a constant, isn't it? I mean, why constant? Later you are going to take beta derivative, isn't it? Pick up. So then apply log here. It's very simple. You add this one to your integration table. Okay, speak up. But anyway, I mean, most of the case, very designed questions are you can somehow solve at that instant. Okay, only way of thinking that you need to develop here. Okay, speak up. So now, I mean, I'm saying even though you don't know this integral, okay, you can solve that particular mathematical problem. Okay, speak up. And look at here. Uh, if you suppose solved that one in the exam, using that one you can solve one more question. Both question exist actually. This question also, that integral also actually. Okay, you eliminate option in that integral. Okay, pick up. Then you know the answer of that integral. Okay, then you solve this problem. Pick up. So log of integral 0 to infinity e power minus beta a x power n dx. Okay, so that's equal to, I'll write minus 1 by n log beta. So plus some log of constant. I'll say this is some constant k. That okay? So then what is this one? Average potential energy. There's nothing but, speak up, minus dou beta of log of 0 to infinity so e power minus beta a x power n dx. Okay, speak up. So that's equal to minus minus plus 1 by n 1 by beta kb t by n. Somebody was asking any general idea for this one. Okay, okay. But here x is 0 to infinity. Okay. In our reef problem, it was 0 to L actually. Check this out. I mean, the reef 7.1, 7.2 something. Am I right? Box 0 to L. Z axis was 0 to L actually. But here it is 0 to infinity. That's why it turns out to be like this, independent of. I mean, we are not saying it's any box or something. Am I right? He said just ideal gas. Speak up. Now look at here, if n equal to 2, that's a quadratic term. Again, you got half kbt somehow. Equipartition theorem answer, isn't it? Even though x ranges from 0 to infinity, not minus infinity to plus infinity even. Is that okay? Speak up. So this is the answer, okay? And in part B of the question, what he's asking? For gravitational, what is the average potential energy per particle in a gas in a uniform gravitational field, okay? So gravitational field means that's a linear potential term, am I right? Speak up. What is this one? Part B of the problem, okay? I'll write my u of x is equal to, so mg into x, am I right? I'll take vertically, vertical upward as a x-axis, okay? Because vertically downward is I'll take this one as x-axis, okay? I'll take this one as g. Somewhere in other plane, okay? zy plane, I will take zero potential. This mgz, okay? This has the idea that you have to take x equal to 0 means potential equal to 0. Am I right? It has some convention actually. Anyway, you will understand this one in classical mechanics. Okay, potential formalism is not unique actually. If you add any constant to potential, uh, force is same actually, because force is, speak up, minus dou u by dou x or dou v by dou x actually. Okay, let us see right now. Let us not get into that one. Again, x is between 0 to infinity. Okay, this average mgz. Okay, in the case when x is 0 to infinity, we found average mz came again. Mgx here. Okay, speak up. X is between 0 to infinity. What is this one? Kb t by 1. It doesn't depend on mg. Huh. Speak up. It doesn't depend on mg, isn't it? Speak up. Okay, let us move on. So that's why it is very important to do all of the exercise whatever I gave, okay? And if possible, if you save time, pick some more this pick Vicalim. Once you could able to do our problem, if you save any time, again pick Vicalim problem and do that one. More Vicalim problem, am I right? Pick up. I picked only MIT, Princeton. Whatever the question that they have asked in bit earlier exam and all, okay? Speak up. That doesn't mean in the next exam they need to ask the same question. Am I right? Speak up. One thing is understanding whatever the exercise that I gave, that's important. And beyond that one, you can do. Once you can solve these things, okay, you can pick other question. This is Princeton question, okay? Speak up. Can you see this one? Consider a heteronuclear diatomic molecule. Okay, these are bit molecular physics word. Let us use that one. What do you mean by heteronuclear? Nuclears are, suppose HCl, okay, HCl, H and Cl, am I right? Both are nucleus are same. And O2, N2, those are homonuclear, okay, or carbon monoxide, CO, heteronuclear. Is that okay? Speak up. HCl, CO, carbon monoxide, HI, okay, HF, these things are there. Hydrogen iodide, fluoride, like that. Okay, speak up. I don't know. But let me take only these two. For an example. Okay, speak up. Consider heteronuclear diatomic molecule with moment of inertia I. He gave moment of inertia. Okay, but that moment of inertia is about an axis passing through its center of mass. That should be understood actually. Is that okay? Pick up. Moment of inertia should be defined with respect to some axis. Am I right? It is passing through its center of mass. Okay, speak up. Only the rotational motion of the molecule should be considered, okay, in the problem. Okay, speak up. So that means, look at here, heteronuclear means, so can I draw that that like this? So he said only rotational motion should be considered. That's why I will replace that one by a rigid what you call rod. We say in molecular physics, we say rigid rotator model. That rod doesn't mean that rod there is any physical rod. It's a bond actually. Bond length is not changing. Why we replace that one by a rigid rod? To say that bond length is not changing, there is no vibration. That okay? He said only rotational motion should be considered. Am I right? Speak up. It's called as a rigid rotator. Okay, speak up. In our molecular physics, it's called as rigid rotator. Speak up. Now, actually, I will just what you call draw this one like this. Okay, speak up. I mean, it is heteronuclear. Okay, speak up. Heteronuclear diatomic molecule. Okay, one is big, other one is small. Suppose in HCl, this is Cl, this is H. Okay, CO, which is O, oxygen is 16. Am I right? Speak up. Oxygen is bit bigger. This what do you call carbon nucleus is still smaller. Okay, there exists a electron cloud actually, but that mass is negligible compared to masses of this nucleus. Can I say like this? Mass of the electron cloud, that is negligible actually. I mean, actually this is two atom which have some chemical bond. Is that okay? Speak up. So there exists electron cloud. Without that, this chemical bond would not arise actually. Speak up. But while talking about this whole stuff, we can discuss only about nucleus, because nucleus is very heavy, electron masses are negligible. Is that okay? Speak up. Now look at here, part A of the question. Okay, speak up. Part A of the question. Speak up. Part A of the question. So shall I make it like this? Part A of the question. Okay, speak up. What is that one? Use classical statistical mechanics, calculate the specific heat of the system at temperature T. Okay, speak up. I mean, in the book he might have done in a different way, but let us use equipartition theorem if energy have quadratic term. Is that okay? Speak up. Now look at here. So it's all our classical mechanics again. I mean, especially Lagrangian and Hamiltonian mechanics. Okay, speak up. If you remind me, I will solve it again. There. Okay, speak up. So now when you have this kind of system, so, or let me take it like this only. Okay, speak up. Suppose if you have a center of mass here. Okay, center of mass would be somewhere here. Am I right? Speak up. Center of mass here. Okay, speak up. And with respect to center of mass, if you take center of mass as the origin, okay, speak up. You can write your kinetic energy, rotational. Okay, if you want to study only rotational energy, he said like that. Am I right? Only rotational motion to be considered. Then you have to go for center of mass actually. If you half I omega square is right. What? But you do you know what is omega? It should be split into three component actually. Okay, pick up. Now what I'm saying here is, when you go to center of mass frame, if you study its kinetic energy, it will be purely rotational energy only. When you see the whole molecule in laboratory frame, it will have rotational motion as well as it will have translational motion. Okay, we shall study much more in in Lagrangian and Hamiltonian mechanics. This will come: motion of center of mass, motion about center of mass. Okay, any rigid body motion can be decomposed into motion of center of mass, motion about center of mass. Here we are studying rotational motion, which is motion about center of mass. Okay, because to study that one, so what we do is, okay, we are going to write our what you call energy expression. So energy expression like half. Okay, with respect to center of mass. Okay, there are two masses. Am I right? Because with respect to center of mass. M1, I would write R1 dot square. Dot, time derivative. Pick up, dot time derivative. Okay, plus M2 R2 dot square actually. Or if I write it specifically, anyway, we can skip this one because this is a classical mechanics discussion. M1 into, can I take this one as M1, this one as M2? Okay, speak up. With respect to center of mass, this is R1 vector. Okay, with respect to center of mass, this is R2 vector. Okay, pick up. Let me write like this. So then half M1, okay, x1 dot square plus x2 dot square plus x3 dot square, or R1 dot square. Okay, R1 dot square, R1 vector dot So that's a velocity. Am I right? R1 vector dot square. Is that okay? Speak up. M1. So plus M2 R2 vector dot square. Okay. I mean, I'm just writing so that you should not feel it is very strange here. Okay. Half is outside. Hmm? Half is outside. Okay. So kinetic energy of first mass with respect to center of mass, kinetic energy of second mass with respect to center of mass. We are not studying any linear or translational motion. We are studying rotational motion only with respect to center of mass. Whatever study we do, that is rotational motion only purely. Is that okay? Speak up. So now look at here. So when you convert the whole thing into spherical polar coordinate, okay, speak up. I mean, it's again conversion of two body problem into equivalent single body problem. Okay, speak up. You will end up with this energy. Okay, speak up. So energy is equal to, speak up, half mu a square. He will write mu a square actually. A is nothing but this internuclear distance. Usually in the textbook they will write r actually, small r, but I'll write a here. Half mu a square, or shall I write r square? I mean, there are some mathematical step in between. It's a conversion of two body problem into equivalent single body problem. Okay, speak up. So this is r. I'll write like this: half mu r square. What is r? Internuclear distance. Okay, speak up. You just write this one. R is internuclear distance. Okay, speak up. So now into, I mean, we are going to convert that one into spherical polar coordinate, okay, into theta dot square plus, okay, sine square theta phi dot square. If anyone have studied Lagrangian dynamics, okay, we write in case of spherical polar coordinate, okay, we write half m r dot square plus r square theta dot square plus r square sine square theta pi dot square. I mean, our kinetic energy of a particle in spherical polar coordinate, we are going to write like this, okay? I mean, anyway, that's a different discussion, okay? Speak up. Now, this r is constant, okay? Speak up. R equal to constant. That's why he took r as a. That's better actually. I mean, for me, r looks like variable, isn't it? Speak up. R equal to constant here, okay? Speak up. Now, if you write Lagrangian, okay? Speak up. I mean, Lagrangian dynamics, okay? If you write Lagrangian, there is no potential energy with respect to center of mass, only kinetic energy. I mean, rotation will happen without assistance of any force, isn't it? Speak up. Rotation, speak up. I mean, uh, it doesn't require any continuous force or potential, am I right? Speak up. That's why Lagrangian is simply half mu r square. What is mu? I haven't written. Reduced mass, okay? This is equal to m1 m2 divided by m1 plus m2, okay? Remind me, in classical mechanics, this problem as well as reduction of two body problem to equivalent single body problem. We shall discuss that one in detail because that comes very frequently, okay? Pick up. So theta dot square plus sine square theta, okay, phi dot square, okay? Speak up. This will be Lagrangian. There is no potential energy actually. Corresponding Hamiltonian would be like this. I mean, this is what I need. I could have introduced this one directly. Corresponding Hamiltonian will be, speak up. This mu r square, we are going to write it as moment of inertia. I. Speak up. Mu r square, that is nothing but moment of inertia. Speak up. So now look at here. That moment of inertia, actually, if you take the center of mass as your axis, okay? I mean, how do you write moment of inertia? Speak up. I mean, that will be m1 r1 square plus m2 r2 square. Okay? I mean, later it is converted into this format. Is that okay? Speak up. Actually, if you take center of mass coordinate, okay? Speak up. Your moment of inertia, that's equal to, speak up, m1 r1 square plus m2 r2 square. You know, I mean, mass into distance from the axis of rotation, the square. Am I right? Pick up. Later, it is converted into mu into r square. R is internuclear distance. Okay, speak up. I mean, it's all the calculation that we need to do, but we are going to take this one. Okay, speak up. So that's why. So let me write this one as half I. half I is just like half mv square. Half I, these things. Okay, speak up. Now that corresponding Hamiltonian will be half. Okay, so correspondingly we define that momentum. Okay, for corresponds to theta, we define conjugate momentum. Okay, in Hamiltonian dynamics, you don't worry. So p theta square by I, okay, plus p phi square by here, okay, I into sine square theta. Okay, this is our Hamiltonian.
What is angular momentum?
These are actually angular momentum only. We say conjugate momentum. It's a generalized theory that Lagrangian and Hamiltonian dynamics is a generalized theory. Okay, whatever p theta, okay, and p phi, okay, they will have a dimension of angular momentum only. They are angular momentum. Especially this p phi is nothing but your Lz Cartesian. If you wish to think in a Cartesian coordinate, it's nothing but Lz actually. Okay, let us see these details in classical mechanics only. I mean, what I wish to argue is if you do all classical mechanics, okay, I mean, Hamiltonian is nothing but energy here. Okay, speak up. It contains two quadratic terms. That's what I want to prove. Hamiltonian contain two quadratic terms. Let me prove in different way also. Okay, pick up 1 by 2I. Okay, I have written. Okay, these are angular momentum only, but we say generalized momentum or conjugate momentum. This is momentum conjugate to coordinate theta, momentum conjugate to coordinate pi. These are the words that are used in classical mechanics. Okay, speak up. So what I wish to prove here is you have two quadratic term in your energy expression, because we can quickly apply equipartition theorem. Even if you use all of those spherical polar coordinate, do the integral, you will end up with the same answer actually. Is that okay? I have other way to argue the same thing. Let me argue in a bit different way. Yeah, running out of time. So, okay, I have this heteronuclear molecule. Why I am drawing only nucleus? Because only nucleus is heavy. You can neglect even electron mass here. Okay, speak up. Is that okay? Speak up. Now, suppose here you have center of mass. Okay, and on that center of mass, if you consider three axes. Okay, if you consider three axes. Uh, I'll take. So which one I shall take? I'll take this one as x, y, z axis. Okay, speak up. I mean, classical mechanics allow us to write our what do you call rotational kinetic energy. I better write E-R-O-T. You better to use this symbol. Okay, this is all rotational motion actually. Okay, I mean, anyway, I hope you understood that point. Okay, so that energy, okay, this rotational kinetic energy, that can be written as Lx square by 2Ix plus Ly square by 2Iy plus Lz square by 2Iz. Where Lx, Ly, Lz are angular momentum components, Ix, Iy, Iz are moment of inertia with respect to respective axis. Okay, this is center of mass. Okay, with respect to respected axis. Speaker. But observe this one carefully. So about this y-axis, if molecule rotates, about this y-axis, there is no distribution of mass at all. I mean, moment of inertia talks about distribution of mass. Am I right? If there is no distribution of the mass, moment of inertia is zero. Speak up. In this case, I mean, in this diagram, Iy equal to 0. I mean, I have to define Iy here, okay, Ix here, okay, Iz here. And that Iy is nearly 0. I mean, almost 0. You can take 0 because here I have bit exaggerated. I mean, this is nucleus and all. But nucleus is actually point mass, isn't it? It occupies very less space actually. And whatever electron cloud, that may contribute little bit distribution of the mass about this axis of the rotation. I mean, suppose if you have axis of rotation, if suppose this what you call point masses are moving. So this is R1, M1, R1, M2, R2. Okay. Suppose M3, R3. Okay. How do you write your moment of inertia? Speak up. That's equal to M1 R1 square plus M2 R2 square, like that. Am I right? As long as you have a masses are a bit far away from the axis of the rotation, you have moment of inertia. If masses are on the axis of rotation, you don't have moment of inertia. Are you getting this idea? Pick up. That's what I'm talking about here. So that's why, because of that, Iy is nearly zero. That's a very good approximation. Okay, speaker. So once Iy is zero, actually, I mean, I will just work out this one. This yeah, suppose Ly square by 2 Iy. Am I right? Speak up. This Ly is also written at what you told I omega y. Speak up. So then Ly square by 2 Iy is Ly square by 2 Iy. That would be, what is Ly square? I square omega y square divided by 2 Iy square. That will be equal to half Iy here. Okay, half Iy, not Iy square here, Iy only. Okay, speak up. Half Iy into omega y square. A written point. I mean, by looking into this one, if Iy is zero, don't take it infinity. It is zero actually. Omega y is what you call angular speed of the rotation. Speak up about that axis. Is that okay? It is zero actually. Okay, so can you write down? I mean, this Ly square. Okay, speak up. You keep this one also. Okay, so here. So what I'm saying is, you better to keep this one also. That okay? I'll come to this one. That's why Ly square by 2 Iy, that term is zero, because Iy is zero. Don't say it is infinity, okay? Because Ly also contain Iy square actually, okay? So that's why your energy, that's nearly equal to Lx square by 2 Ix plus Ly square by 2 Iz. Actually, these coordinates are your choice. You could have chosen this one also, z axis, okay? Lz, yeah, Lz square by 2 Iz, okay? This part is zero. In this way also, you can argue there are two quadratic terms in the kinetic, in the rotational energy. I mean, you need how many, what is the energy term, am I right, to apply equipartition theorem? First part of the question. Is that okay? Speak up. Yeah. So that's why, I mean, average energy would be, can I say like this? I mean, now I will go to first part of the problem. Yeah. Part A. Okay. Speak up. Part A continued. Okay. Speak up. Somehow, part A continued. Rotational energy contains two quadratic terms. Okay, speak up. That's why average energy per particle because of rotational motion. What is this one? Half kbt plus half kbt. Okay, actually they will find what you call partition function and all. Actually, that's not required. Okay, I mean, in the textbook he may find using this idea. Okay, using this polar coordinate idea, he will find partition function. Okay, integration with respect to dp theta dp phi, d theta d phi, like that. Okay, speak up. I mean, just like, I mean, how we did partition function dx dy dz, dpx dpy dpz. They may find that one that's not required. We can directly apply equipartition theorem. Okay, pick up. It's all quadratic term. Is that okay? Speak up. Now, average energy per particle, that's nothing but kb into t. Okay, speak up. Then, so specific heat per particle, can I say like this? How to write? I don't know what he writes here. What is the problem number? 2038. Yeah, he will keep it as it is actually, but actually specific heat is the quantity of interest, isn't it? Hmm? So specific heat per particle, can I write specific heat or what you call heat capacity per particle or specific heat per particle? Heat capacity per particle would be better.
In the question he has asked specifically.
Specific heat, but per particle only, okay? Speak up. That is per particle only. That's why the confusion, okay? Specific heat of the system, but he is expecting per particle only, okay? Total number should be multiplied. That's it. Okay. I mean, there will be no confusion in the options. I mean, if MCQs are designed, but he is writing per particle here. Okay, in his solution. Okay, speak up. So that's why ultimately I will write small CV. Okay, speak up. That's nothing but kV. Hmm? Speak up. Suppose if you take so total average energy for Avogadro number of particle. Okay, for 1 mole of the substance. Okay, you can write Na kBt. Then specific heat, molar specific heat, you can write Na into kB. That's nothing but R. Okay, speak up. But remember, it is contribution by only rotational part. If you take diatomic molecular gas, it will be having translational also. It may be vibrating also. Okay, we shall consider that one. Okay, that's I think I have discussed that one in thermodynamics. Okay, that part. Okay, diatomic molecule is specific heat at different temperature. Okay, but we can discuss that one here only. Let me see if we can discuss here only. Okay, speak up, because that's also a bit important question. Okay, remember this is rotational contribution to specific heat. Can I say like this? That's better, because we took only rotational part of the total motion of that diatomic molecule. We didn't consider its translational motion. We didn't consider a vibrational motion. Okay, pick up, and we shall see when we consider all of those three what would happen to specific heat. Okay, in a separate class. Okay, so that's why read the question very carefully. He specifically mentioned only rotational motion of the molecule should be considered. Okay, pick up. Part A of the question is done. Now, in part B of the question, speak up. In part B of the question, speak up. Again, you need to consider it quantum mechanically. Is that okay? Speak up. So then your Hamiltonian will be, speak up, L square by 2I. Am I right? Again, I is equal to, you can write I as mu R square. R is internuclear distance. Okay, speak up. R is, oh, mu is nothing but m1 m2 divided by m1 plus m2. You don't have to take atomic mass. You can take even nuclear mass. Electron mass can be neglected here. Okay. Speaker. Now, if this is the Hamiltonian, okay, speaker, what are the energy eigenvalue? What are the eigenfunction? Or it is actually L vector square actually. Okay, speaker. L square eigenvalues. So your energy, since it is single particle energy, I'll write epsilon. He may take capital E. I'll take epsilon. Okay. Oh. Okay, energy, that's equal to this h bar square L into L plus 1, isn't it? Divided by 2I, L square eigenvalue divided by 2I. I told you, am I right? If any operator multiplied with any constant, eigenvalues are multiplied with constant. What is L square eigenfunction? Spherical harmonics. Okay, your wave functions here, theta phi, okay, depends on L and M. That's nothing but your spherical harmonics. I mean, this is that Griffith's problem, isn't it? I mean, in that fourth chapter. Speaker. This is our energy, okay? But he has taken J. That's actually in molecular physics, okay? We don't take L symbol, we take J. But you should not get confusion with our atomic physics J. Atomic physics J means total angular momentum quantum number, am I right? Here, again, this L is nothing but 0, 1, 2, and so on. It's all our legendary differential equation, the the restriction put by legendary differential equation solution actually. I mean, this contain legendary polynomial, associated legendary polynomial and all, isn't it? And m value is, speak up, minus L2 plus L in integer step. Is that okay? Speak up. Now, speak up. Yeah, what he has taken? He has taken J here. Okay, I will take L. Is that okay? If I change the symbol, but he put J equal to integer only, not half integer. Half integer won't come. It's all pick up. It's all spatial part. Is that okay? That half integer came because of spin part. We are not talking about anything related to spin, degree of freedom and all. Okay, what we are thinking? I mean, it's just a rotational motion. Okay, speak up. Are you getting this idea? That's why, I mean, according to quantum mechanics, L symbol is better. But in molecular physics, they replace this L by J symbol. Not only small j, capital J actually, you will see, okay, in many textbooks. Okay, pick up. Anyway, I will keep L only here. Okay, pick up. I will keep L only here. So it will have degeneracy, am I right? Energy depends only on L. But your wave function, that depends on M also. How many M are there for each L? Speak up. For each L, pick up, there are 2L plus 1 M values minus L2 plus L, isn't it? So that's why. So EL R, pick up, 2L plus 1 fold degenerate, pick up, 2L plus 1 fold degenerate. Okay, or I will write GL. Okay, that's equal to 2L plus 1 or G of EL. G of EL, degeneracy of EL state. I'm going to write 2L plus 1. Is that okay? Speak up. I think we have already written this one, okay, somewhere. So now you have to write partition function. Single particle partition function once energy is known. Okay, I mean, why I have written wave function? Because degeneracy, it comes because of wave function, am I right? Energy depends only on L, but wave function depends on M also. There are 2L plus 1 orthogonal state corresponds to one possible value of L, isn't it? Speak up. So that's why Z is equal to summation over actually EL or L, because E depends on L. Okay, L equal to 0 to infinity. So G of EL, okay, e power minus beta EL, isn't it? Speak up. That's equal to, so summation over L equal to 0 to infinity. So 2L plus 1, okay, e power minus beta h bar square by 2I L into L plus 1. Okay, I don't think this series can be evaluated. I don't think so. No, it is convergent, but I don't know whether we can have well-defined what do you call answer here. Okay, speaker. Give me a minute. Okay, can you guys hear me on Google Meet? Speak up. Let us finish this out. Now again, I mean, suppose if you take this one. What is that? Uh, Average energy per particle, that's equal to minus dou by dou beta of log of z and all. Okay, he will evaluate that one, but it is too lengthy. I mean, you can write that one. Okay, yeah. So you can write these things, but I don't think you can evaluate. Okay, now look at here. Here comes the what you call limitation of our whole system of education. Okay, wait a second. How it is transformed to education? I was discussing about computation. Okay, pick up. Okay, whatever you can solve by hand, you solve. But whatever you can't solve, you can use computation. Am I right? You can take L equal to 0 to maybe computer may go up to 1000. E power minus beta into some 1000 into 1000 plus 1. That is negligibly small. I mean, higher order you can neglect. Am I right? Computer will give you very good value actually. I mean, if you can't do it by hand actually. Okay. And there are very less problem we solved by hand. Okay. Whatever in the textbook actually. I mean, naturally, there are a lot of things where that we didn't solve. I mean, it need not be always well-defined function actually. Okay. Speak up. I mean, you can use computer to make some numericals out of it. I mean, take some HCl molecule, take M1, M2 values, okay, I is known, okay, beta, KBT, take some temperature, you can evaluate this one. Or keep temperature variable, okay, somehow, okay. Yeah, anyway, that's a different part. I mean, this is where we need computers, okay. I mean, harmonic oscillator, we didn't face this one, am I right? I mean, there was no degeneracy and it can be written as a geometric progression, I think, isn't it? Speaker. Yeah. So Judd here, okay, speaker. Now look at here. Okay, let me write that one. Let me write that one from the textbook, okay. So this is equal to summation over L equal to 0 to infinity, okay. So 2j plus 1, okay. Since you take log and then beta derivative, okay. So h bar square by 2i g not j again I'm reading the textbook. 2l plus 1 h bar square by 2i l into l plus 1, okay. So e power minus beta h bar square by 2i, okay, l into l plus 1, okay, whole divided by this is a derivative. I mean, this is a numerator part because 1 by z would come here, right? Speak up. Divided by that partition function summation over l equal to 0 to infinity. So 2l plus 1 e power minus beta h bar square by 2i, okay, l into l plus 1, okay. Speak up. So now look at here, but I mean in the part C of the question,
Just give that sum.
huh?
Just give that summation.
Using quantum statistics, derive the expression for partition function and average energy of the system as a function of temperature. Do not attempt to evaluate this expression. Okay, speak up. I mean, I was thinking whether it can be made arithmetico-geometric progression like that. You are saying something. You can write it as a derivative.
Sir,
Huh.
that would be derivative of L, sir. We cannot take it outside. If it is
Oh,
derivative
it
of
is.
beta, we can take it outside.
Okay, derivative with respect to L, it will be inside only because summation over L actually. Hmm, hmm, that was different trick actually. Beta derivative. Okay, speak up. So anyway, so part C of the question, by simplifying your expression, okay, in part B, derive an expression for specific heat that is valid at very low temperature. At very low temperature and at very high temperature, we can do something. Okay, speak up. So now what we do is, okay, at very high temperature it would be bit different story. Let me start taking low temperature. Uh, Pick up low temperature. That is part C of the question.
Yes.
Yeah, C. Okay. So low temperature limit. Okay. Low temperature means, okay, I mean, how low it is? Again, you have to compare with the parameters. of the system actually. Okay, speaker. So what comes in this exponential? Beta h bar square by 2i. L into L plus 1 is dimensionless. Okay, pick up that beta h bar square by 2i is very large. Okay, speak up. So beta h bar square divided by 2i is very, very greater than 1. That means h bar square by 2i is very, very greater than kBT. I mean, temperature is very less. I mean, it's all should be compared to some system parameter. I mean, I told you, am I right? 1 Kelvin, 300 Kelvin, 3000 Kelvin. Which one is higher, which one is lower? Comparative, am I right? You have to compare with h bar square by 2i actually. Okay. In this particular problem, which is higher, which is lower? This is how you have to, so check this one. Okay, speak up. Yeah. Now, if this is very high, we will go to partition function itself and neglect higher order term. I mean, if this is very high, e power minus this whole quantity is low, am I right? And exponential always dominates actually. And again, when you go to higher and higher term, L is also increasing. Not only along with this beta, you have one multiplicative factor that's also increasing. So you can neglect higher order term. What it does is, I mean, whenever we do that kind of approximation, we take first two term. I mean, we take the term which has a variable. I mean, to make it very simple. Okay, so that's why actually this Z we are going to write that's nearly equal to Z was equal to summation over, speak up, 2L plus 1, okay, e power minus beta h bar square by 2i L into L plus 1, okay, L equal to 0 to infinity. By applying this one, we write Z is nearly equal to first two term L equal to 0, 1 here, okay, e power 0, 1 plus L equal to 1, 3 here. E power minus beta, 1 into 1 plus 1 is 2. Okay, so 2 got cancelled. Beta h bar square by I. H bar square by I, isn't it? Pick up. We take Z nearly equal to like this. Yeah, that's right. Okay, from that one we will find average energy. That's equal to minus dou by dou beta of log of Z. Okay, that's equal to this is a question in some previous exam. They didn't ask average energy, they asked Helmholtz energy. That's equal to minus kb log Z plus beta into average energy. They asked what you call Helmholtz, I mean minus kb or plus kb?
Minus kb, sir.
kbt, t also should come.
Minus kbt log Z.
Minus kbt, okay, minus kbt log Z plus beta into average energy. I mean Helmholtz energy per particle. I mean, they asked this one in this regime actually.
Sir, beta is not there. It's only minus kb.
Okay. Why this is entropy actually?
Yes, sir.
Minus kbt log of Z actually. Yeah, I remember now question. Question is you have to take that low temperature limit. Then this log Z contain two factors. Log of 1 plus x expansion we know. You have to apply that one again. That's how they design the question. Okay, you should just remember this formula. You can find partition function at low temperature. Then I mean once you have low temperature, I mean look at here. In this one there are many terms, but we made it as simple as possible by keeping the variable part. That's what I told them, right? In any approximation, don't make it constant. Don't again neglect this one and make it 1. Derivative will be 0. Speak up. So what you need, I mean, not only derivative, log Z is also 0. Okay, speak up. So that's why you while if they ask any what you call approximation, I mean, it should come by practice that you should make it simple expression, but variable should be kept. Okay, variable should be kept over there. Speak up. So then look at here. I mean, that's what they were asking here. Okay, they were expecting that one. Not only not over here. You have to substitute. Then log of 1 plus x expansion first term. I mean, in this one, log of 1 plus x, I think First term is x minus some x cube by something will come actually. First variable term is x actually. They were asking that term actually. Okay, ultimately. Okay, that's, I mean, you have to see the option and keep doing the problem. Okay, then only will get into the right one. Okay, speak up. Now I will just write this one quickly. Okay, speak up. I will save some time. So 3 h bar square divided by I. Okay, so e power minus beta h bar square divided by I. Okay, 1 plus 3 e power minus beta h bar square divided by I. Okay, I think the specific heat is too lengthy. I mean, u by v. I mean, you need to do one more derivative, right? Minus 1 by kbt square dou by dou beta of, am I right? I am getting confusion. Numerator or denominator?
Sir, this is right.
Yeah. So that is equal to, I'll write it directly. Okay, 3k. So beta h bar square divided by I, the whole square, e power, somehow plus came. Okay, he manipulated, I think, beta h bar square divided by I whole divided by 3 plus e power beta h bar square divided by I, the whole square. Is that okay? Speak up. Give me 1 minute. Speak up. He kept as it is. I mean, look at here. Now they don't design question like this because you want to type 4 option, you don't know how much time it will take in LaTeX, isn't it? I mean, they don't make this lengthy. What they did, they went up to this one, then log z, that contain again one more approximation, so that answer is small only, not this big. Okay, speak up. Anyway, so this another part of the problem. What is this one? A, B, C, D, D. Okay, part D of the problem. Okay, speak up. Part D of the problem. So in the limit of high temperature, okay, high temperature limit, okay, high temperature limit, that means, so beta h bar square by 2y, that is very, very less than 1. Temperature is high means beta is very low, isn't it? Speak up. So in that limit, actually, high temperature limit, look at here. I haven't written this EL. EL is equal to, what is this one? H bar square by 2I into L plus 1. Am I right? Pick up. So these are like this. This is quadratic in L actually. Okay. This will vary like this. Okay. Pick up. L equal to 0, L equal to 1, L equal to 2 levels. Okay. Energy level. If suppose your KBT is very high compared to this energy gap, high temperature limit, then, I mean, these energy gaps are not so appreciable. You can go for classical statistics, isn't it? But look at here how he did the problem. He didn't go for classical one. Okay, he, what you call, he has taken this partition function only. Okay, so this partition function only, whatever partition function we have, that's equal to summation over L equal to 0 to infinity. Okay, so 2L plus 1. Okay, e power minus beta h bar square by 2y L into L plus 1. Am I right? He converted this one into integral by taking this approximation. I mean, see, L looks like continuously varying when in the perspective of KBT, thermal energy. Okay, speak up. That's why he will write Z nearly equal to integral 0 to infinity. So 2L plus 1, because summation is over L only, and L do not have any dimension. Okay, L do not have any dimension. E power minus beta h bar square by 2y L into L plus 1 into dl. into dl. Yeah. Actually, the idea is once kbt is higher, you go for classical, I mean, equipartition theorem. That gives kbt. This also gives kbt. I mean, okay, so it is a summation, okay, over very large L value where the gap is not very negligible. Then that summation is converted into integral actually. That kind of idea, okay? I mean, if you think pure calculus, okay? Now, this, how do you evaluate? No, you better to take a derivative, no, beta derivative.
L square plus L.
Okay, okay, L square plus L. One is Gaussian integral, other one is, I think it can be done.
That will take some.
Okay, okay, okay. You can substitute. Yeah, yeah, exactly. 0 to infinity. So 2L plus 1, okay, e power minus beta h bar square divided by 2i. The next problem was also substitution actually, that harmonic oscillator. So what is this one? L square plus L dl, okay. L square plus L is equal to z, okay. L square plus L is equal to z, okay. So 2L plus 1 is equal to dz, okay. Speak up. So that's equal dl, okay. 2L plus 1 dl is equal to dz, okay. Speak up. So integral 0 to infinity e power minus beta h bar square by 2i dz simply. Okay, this is just reciprocal of z coefficient. Am I right? 1 by h bar square by 2i or 2i by h bar square, 2i by h bar square into 1 by beta. Am I right? Z. E is equal to minus dou by dou beta of log of z. I hope this is 1 by beta. Do it again. That's nothing but kbt. It all went to our equipartition theorem answer. Speak up. Yeah, let us close here. I have some work. Now, okay, this is rotational part. Okay, you just do it again. You remember, I will use this one to discuss diatomic molecular gas, specific heat of diatomic molecular gas. Where rotational part is one of the part. We have to discuss vibration also. We have to discuss translational motion also. Okay, yeah. Each and every problem gives you lot of ideas. Okay, speak up. Solve it neatly. Okay, what I would suggest is, if you suppose later, not now, right now, just concentrate on my homework. Later, if you suppose if you wish to do more Weichel problem, don't choose Weichel. You choose this Sidney B. Cohen. I mean, a guide to physics problem. Can you write down? A guide to physics problems, part 2. Okay, pick up. Okay, part 2. I'll write only one author name. 3 authors are there. Okay. I mean, I would suggest you to look into this one only for problem and answer key. But if you want any solution assistance, this is better than Weichel. Solution assistance. Okay. Weichel solutions are not logical. I mean, it looks like what do you call? I mean, directly taking and answering. Okay. Not even Jugaad. Jugaad is different. Jugaad is innovative. So this contain bit good explanatory, but symbols are very headache. Okay, just like he take tau, which is equivalent to kbt actually. Okay, speaker. Yeah. Okay. We shall close this session. We will be meeting tomorrow morning. We shall continue and we shall save some time for this problem. Okay, tomorrow morning. Okay. Yeah. ಅಲ್ಲ